the hérisson coupler. In construction we also speak of a sleeve, or more simply a rebar connector. But I know that when you're not in the trade, the object may appear insignificant. However, to get where it is today, it's been on a long journey, abundant with discoveries, technical progress and a little luck along the way. With a little audacity, we could even say it all started with the Romans. In the shade of the Colosseum, our distant Latin cousins concocted a surprising blend by mixing limestone, clay, volcanic sand from Puzol, and water to produce mortar, the ancestor to concrete. Well, it's true, the recipe got a little lost in the ramblings of history. It resurfaced a few centuries later, directly in the head of a certain John Smeaton, a British engineer. Other engineers were then involved in improving this recipe, and today, to make concrete, well, firstly you need limestone, clay and a pinch of gypsum. What you produce from this mixture is cement, which is then mixed with water, sand and gravel to make concrete. But let us return to the Age of Enlightenment, because during this period another recipe was being prepared in the blast furnaces, the recipe for steel, a subtle alloy that with a few extra grams of carbon would make iron prehistoric, and with a few grams less would relegate cast iron to the weights room. Well, okay, I'm exaggerating just a little, but the right dose of carbon enables steel to be much more resistant than iron and much less brittle than cast iron, which makes it perfect for many applications, especially in the construction trade. So you see, concrete and steel begin to meet on the worksite at the end of the 18th century. At this time they're only just meeting, because in all honesty they ignore each other very successfully for several decades. And yet, concrete and steel have everything they need to get on well. Concrete is not so expensive and resistant to compression, but a lot less resistant to tension. Steel is very resistant to compression and tension, but costs an arm and a leg. I think you understand. By casting concrete onto a small quantity of steel, well, we can obtain a material that's resistant to compression and a tension and a material which is cost effective. We're now at the end of the 19th century and reinforced steel has just been invented. For architects and engineers, this new composite material is a godsend. We're now able to build even higher and even bigger, so we need to find even longer bars, and that's where the snag is. But that doesn't hold us back. We just need to put the two bars together end to end. And in order not to lose resistance, we just need to overlap the two bars. This is called lapping. It's essential here that lapping ensures the same resistance as if the bar were in one continuous piece. This means the length of lapping must be about 50 times longer than the diameter of the bars. In fact, 30 to 60 times more to be more precise. It all depends on the resistance of the concrete cast around the bars. In other words, if the diameter of the bars is 4 centimeters, then lapping will be about 2 meters. All this could happily have continued in the world of concrete and steel if it hadn't been for a slight problem of bonding. I say slight, however. Concrete, as we said, doesn't resist well to tension. In a beam such as this one, the load is transferred from the concrete to the rebars in areas under stress. In other words, areas subject to tensile load. Once again, the two materials must bond perfectly, one to the other. At the beginning of the 20th century, well, at this time the rebars used, as you can see, were perfectly smooth, and the concrete was unable to bond to this smooth surface without a raised pattern. If the steel doesn't take up this stress, the concrete, which is unable to do it, will begin to crack and the whole beam may collapse. To resolve this problem, bonding bars were produced with profile patterns. In other words, with this raised pattern, the new bars perpetuated the tradition of lapping. The technique is proven and is still used today in many work sites. All these bars sticking out of walls are waiting for lapping. Once again, developments could have stopped here. However, on work sites, in the shade of a few impassive cranes where concrete mixers relentlessly mix their rubble and sand, under the benevolent eye of a few placid tractor loaders, vaguely perturbed by the soft rumbling of the stuttering pneumatic drills, someone was heard to say that it wasn't enough, that the technique could be still further improved. In fact, to build a wall, concrete is cast into formwork like this over steel rebars. Once the concrete is set, the framework is removed. However, to introduce the rebars required for lapping, holes must be drilled in the formwork, which cannot be reused subsequently. Not very practical, and masons all agree that it's a long and complicated process to implement, especially during construction of big structures. To resolve this issue, a connector was developed, a connector that is used to connect two bars placed end to end. There are several types of connectors, like this one, or this one, or the Hérisson coupler. The advantage is that with such a device, from now on, once formwork is removed, all you need to do is screw on a bar and continue to work on site. It's much faster, formwork doesn't need to be drilled, and this rebar coupler saves meters and meters of lapping steel. In short, the coupler is a godsend, and you may well ask yourself why it wasn't thought of earlier. All said and done, it's true that the tool is not child's play. To ensure the same resistance as lapping, this part must be robust. In fact, a connector must be more solid than the bars themselves. And before it arrives on a work site, well, each new model is subjected to a whole set of merciless tests. A real ordeal. Here, the two bars and the connector that connects them are put under tension. A force of 600 tons is exercised at each end, a lot more than would occur in reality. To pass this test, the bars must break before the connector. And it's not finished there. Even if it's used in regions that are calm, well, our tenacious little connector must also be able to withstand the violence of an earthquake. It's compressed and stretched at the same time, over and over again. Resistance to fatigue is also tested by a pulling action 2 million times in succession. You can see that it's only after a very long ordeal that a connector achieves the right to be cast in concrete, to ensure utmost safety standards, not the slightest weakness is tolerated. Until today, all connectors used were smooth, just like the bars in the past. After all, we could say that connectors only represent a few centimetres, and that they don't play a great role with respect to the bonding of concrete and steel. But today, buildings are more and more complex. They need to be more solid. Many smooth connectors can be found side by side in structures interwoven with rebars. This creates an area of weakness. For certain buildings, e.g. nuclear power plants, this cannot be envisaged. The building requires a real coat of chainmail. That's why a new connector has been developed, a connector that we now call a coupler, the famous Hérisson coupler. Using this technique, the bonding bars are upset. That means they're compressed at one end to increase the diameter. The density of the material increases, making the metal more resistant in this area. They are then threaded to be able to screw into the coupler. Two rings known as lock nuts are then used to lock the bars on each side of this new rebar coupling device. The coupler is not only smaller and lighter, it's also more resistant than the other connectors. It has improved bonding qualities, especially with its raised pattern, from which it takes the name Hérisson, meaning hedgehog. As a result, concrete and steel have never been so intimately coupled. All you really need to do is think about it. Moreover, I ask myself why the Romans didn't think about it earlier. It must have slipped their minds.